yourself is not as easy as it sounds. Framing, focus, and stability are hard to manage when you don't have a cameraman. And that's where the problems lie. While object tracking has been studied extensively in general, only a few targets have been specifically studied for cell shooting. So we don't know yet which trackers works best in this cell shooting scenario. Actually, on limited devices, like common laptops or cameras, where GPU acceleration may not be available. And that's the gap our research aims to address. Objective is to evaluate and compare three representative trackers, KTF, CRT, CFRT, and CMFT, in the context of automatic troubleshooting. We want to see how they balance speed, robustness, accuracy under real-world conditions, and identify which tracker is most suitable. KCF is a lightweight correlation filter tracker, which is extremely fast but less robust. CFRT improves on KCF, handling occlusion and field variations better while running in real time. And lastly, CMFT represents deep learning based approaches, generally more accurate but heavier computationally. So even though direct cell shooting studies are rare, we can still learn from prior tracking research. KTF studies shows that correlation filters are very efficient, but they struggle with occlusion at large scale changes. CSRT has been used in embedded systems, showing improved robustness compared to KCF, and though with lower speed. And lastly, SciMFC has been widely tested on LAFWP benchmarks and other benchmarks where it consistently show higher accuracy, but a higher computational cost. So from the data part, we see common pattern here. Faster trackers are usually less accurate, and the more accurate trackers are often slower. And what's missing here is a clear comparison in the context of cell shooting, where there's just one person moving around, no cameraman to readjust if the tracker fails, and often only a regular laptop or camera without powerful hardware. So for our experiments, we used 20 sequences from the person category of LAS data set with over 50,000 annotated frames. This data set was selected due to its diverse chunking, where it's including varying lighting conditions, complex backgrounds, rapid object motion, occlusion, and object rotation. Oh, and it also provides a robust benchmark. So we took KCS, CFRT, and SciMFC and measured three metrics. The first one being mean IOU or overlap accuracy, precision at 0.5 for consistency, and frames per second for speed. All experiments were run on a regular laptop without GPU acceleration to represent what everyday users might actually use. So, what did we find? SciMFC achieved the best accuracy with IOU in 0.321, precision at 36.48%, but only 5.6 FPS, which is low on IOU. And the next one is CFRT, which came in second in terms of accuracy, with IOU at 0.216, precision at 20.919%, and 17 frames per second, which is still usable in real time. And lastly, KCF. Even though it was the fastest with 109 frames per second, which is very efficient, its accuracy was lowest at IOU only 0.126 and precision at 14.39%. So the trade-off here is very clear. KCF gives you speed, SciMFC gives you accuracy, and CSRT gives you the middle balancing. As you can see from pictures here, so this isn't just in numbers, you can also see it in behavior, where KCS tends to drift when the target changes, CSRT tracks more steadily, and SciMFC stays closest to the real object. But we should also remember that there are limitations on the research where LANOT dataset protein sequences are very tough. With fast motion, blur, and occlusion, and even top trackers only get about 50 to 60% precision. Plus, our models were fine-tuned, so we're looking at the basic performance before any fine-tuning. Okay, so all things considered, we can deduce that C is the most accurate but slow. CSRT balancing speed and robustness, making it most practical choice for everyday users, and KCF is only useful when speed and efficiency are top priority, essentially sacrificing accuracy. C is best when accuracy and robustness matter the most. CSRT is good for practical middle ground for everyday use with limited hardware. KCS is only suitable when speed is the main priority, then at the cost of accuracy. And for our future work, we can expand testing to a larger data set. We can run experiments on embedded devices, evaluate newer trackers which push accuracy much higher, and explore hybrid strategies such as finding a fast tracker with periodic deep rechecks, and lastly, run user studies to measure how well these trackers maintain practical payment quality for real computers. That is all for my group. My name is Helena Picahaleo and my partner, Leonardo Jayapal. Thank you. Okay, good morning everyone. Let me introduce myself and my partner. My name is Jessica Valencia. This is my partner, Yehuda. So today we are going to present about our research entitled Zero Stress Level Detection using random forest, 3D machine, and a hybrid model based on user text input. So why did we choose this topic? First, we have to know that volatile communication defines stress as a state of worry or apprehension caused by a difficult situation. The problem is, based on American Psychological Association, in 2023 survey, there is age group in 18 until 34 feel the 67% stress make it hard for them to focus, and 55% feel respondents feel that when they are stressed, they can bring themselves relatively, and 47% feel that once they are so stressed, they can function. In addition, based on a survey in 2024, there is increasing number of people feeling stressed from 40% to 79%, with 50.3% is student and 49.7% is full-time work respondent experiencing daily stress. To handle this problem, there are various studies have been conducted with the aim is to detect each individual stress level to prevent any increase that may negatively impact their health. So their solution is using AI machine learning with various models like random forest, reducing machines, water processing, K-nearest neighbor, decision tree, logistic regression, and others. Also, they use various accuracy metrics like accuracy, precision, recall, advanced score, methodological error, mean absolute error, and others. But the question is, which optimal approach within various model and evaluation metrics that better to detect stress level for students? So our study proposed a solution, but where did the solution came from?
Next to the literature review for our study. This is for stress detection. We have the top three models which are is very mostly, and of course, we have all over 85%. And this is for student stress detection. Top three model is China forest with Melatonin, Assistant 3, and forest with D, and all over 90%. And then this is for precision and recall. Precision has top three model which are very acoustic, forest, logistic encryption, and all over 70%. And this is for recall. This is which are station 3, very acoustic, this encryption, and all over 74%. And this is for advanced core, which are is division 3, very acoustic, logistic encryption, and all over 76%. It is a GVM because GVM is a model that's defined by evaluation result on these metrics of accuracy, recall, precision, and point score for stress detection compared to other model. And we choose RF because from 30 analysis study, 14 journals use RF for us, but only 6 journals say RF the best performance result. And this is the important study for our result. This study is used GBM and hybrid model to combine and GBM for stress detection. This study is using studying process, and this is study show high accuracy result for each model and the hybrid model. The best model is hybrid model. And as we go to the methodology, we use data set from Kaggle. The name is student stress factors comprehensive analysis, and the target attribute is stress level. And the model we use is the first is gradient boosting machine because the gradient boosting machine uses a boosting technique that combines its three sequentially and is known to be superior in terms of accuracy and focus on improving the prediction model gradually based on previous error. And the second is random forest because archive uses a weighing base to sample through for it to get the final output result and is known for its superiority in efficiency and stability for prediction. And the third is hybrid model because the hybrid model with different learning are set up because of their respective performance in terms of accuracy, efficiency, and stability with some method. And for the hybrid model, we use a self-voting method. So each model using this hybrid model will predict the change for each class. The change are then average for the class. The class with the highest average will be selected as the prediction result. And for data processing, we processing like usually we use a Python with Google Colab. We handling empty data, we encoding data, we checking normal distribution, handling balance data, and check attribute correlation. For training process, because the dataset is controller, we split the dataset into 80 to 20, 80 for training and 20 for testing. And we use Kepler validation, which are 3, 5, and 10. This is for hyperparameter we use. And the evaluation, we use a precision and recall because precision we already using false positive error and recall we already using false negative error. And for other metrics, we use F1 score and pricing. Pricing we will compare to the need. Information rate is statistical cost that can absorb wherever accuracy result is significantly for government. And to check overfitting, the study compared to mean cross validation result with a trend test and test set evaluation result. A lot difference indicate overfitting.
Okay, next for the result and discussion, we got that all evaluation results are above 90% for each model at K-value. And we can see that Random Forest is the best model with the highest evaluation result on the testing data for each metric and K-value. And the other two models have the same evaluation result for each K-value in the testing data evaluation. And this is the result of overfitting check. This diagram is get from difference between the testing data and training data evaluation results. We can see that there is a quite similar pattern in for each diagram. But for example, we choose F1 score. In F1 score, blue bars show that random forest show a small positive differences for all results. It indicates good generalization to active data. And RF is still the best model showing overfitting because it's stability. And for GBM and hybrid model, show positive difference for K in 3 and 5, but there is negative difference for K in 10 because both model use GBM, which is known for its high accuracy, but this also makes them more likely to overfit. And that's why we see negative result, meaning the model learns the training data too well, but doesn't work as well on the test data. And for the no information rate, there's a very large difference reaching more than 30%. It means that these three models are significantly good for detecting stress level, including random forest as the best model. So the evaluation results and the best models found in this study are different from other studies because of differences in the data set we use and methodology we use. For the conclusion, our study has a goal to prevent increasing stress level for students using AI, machine learning, with random forest, grading machine, and hybrid model. After we did some processing in the data, we got random forest as the best model with precision, recall, and advanced score, reaching over the 98% in all K values. And last, the accuracy score for random forest compared to the clear accuracy score is more than 30%. It indicates that this model is significantly good for detecting stress level without the potential of underfitting or overfitting. And for the limitation, the study just used a version of Google Colab and the future work, yet the researcher can use larger data set and explore the boosting model. This is our references. Sorry if there are any mistake from us. Thank you for your attention.
But some of you may not know what this means. Some of you might be wondering, what is model poisoning? What does it do and how do we prevent against it? Well, model poisoning is a relatively new thing. As you can see, there are many articles written in 2025 about model poisoning from Nature Medicine, Teletype, and Telephonic Method. All of this shows that your AI models are endangered of model poisoning. Now, our research shows that integrating multi-stage robust training with DMAC for reinforcement engagement defense. It might get a bit more technical in the future, so bear with me. Now, before we get into it, there are a couple of things that we should know. First is what is federated learning, what is model conflict effect, and what is our innovation. Federated learning is a machine learning method in which multiple clients collaboratively train a shared model using their own local data without sending the raw data to the server. What this means is that your model is shared to different clients all around the world, training them with your own set of data, your own PC, and then sending the results to server. Now, what is model poisoning attack? Model poisoning attack is where malicious clients will inject corrupted model update to harm the global model performance. What it means that when your model is shared to other people, some people will try to corrupt it and send it to your own global server, making the performance to be decreasing, to decrease the performance. Now, our innovation is a novel and robust FL aggregation framework design for more comprehensive protection against adaptive model poisoning attack. Here we will implement DMAC detection and three-layered model. Now, as I have said earlier, federated learning is a framework distributed model training. Here we can see that the support initiates your models and then share them to other clients, which will then train with their own set of data at your personal computer. And those clients will then share their updates, and those updates will be aggregated to your cloud or server. And this process will repeat itself automatically. Now, what is malfunction attack? It's a major vulnerability in FL. It is the potential for malicious clients to launch poisoning attacks with the goal to stop the process, not to stop the process, but to corrupt your model. Now, there are two types of model poisoning, targeted attack and untargeted attack. Targeted attack aims to compromise a specific task, such as creating a backdoor in the model, where untargeted attack affects all of your models, so it does not have any specific targets. Now, how do we prevent it? The first way is anomaly detection techniques. These methods focus on identifying and isolating malicious clients by analyzing their model updates for suspicious behavior. Our research shows that DMAC, microintegration, and clustering and advanced framework are often used. For DMAC, it uses a Graphcore metrics to measure the L2 norms of client gradients. It may sound a bit technical. Here's a simplified version. So they have a metric system to measure how wrong is the updates. And if it exceeds certain levels, it will be signed as malicious. For micro-integration and clustering, they use techniques such as GMM or Gaussian mixture models and DBSN to group similar updates. So if they're all malicious, it will be grouped together. For advanced framework, some system combines multiple techniques such as autoencoders and LSTMS, analyze and filter poison data based on learning patterns. So here we learn the patterns of malicious clients and then we filter them out. The other method is robust aggregation techniques. These techniques modify the server-side aggregation process to minimize the negative impact of malicious updates. If on the previous step we analyze the data, here we analyze when the server aggregates those updates. Here we found that dynamic clustering, ROMOA, FedRDF, and FedDev would be the most commonly used. Dynamic clustering groups similar client updates together and then perform a separate robust integration within each group. So similar to this, to the previous one, which is micro-aggregation and clustering, full clustering groups them together and then aggregates them all at once. Well, meanwhile, use a sanitizing factor or a weighter, such as like DMAC, adjusted by temporal similarity and historical behavior to reduce the influence of malicious updates. While FedRDF leverage the Fourier transform to filter out malicious descriptions. And FedDev uses in fact, a model that counters adaptive attacks by reducing attacker optimization cost functions. FedDev is run by patterns, so it will recognize the malicious patterns and will also filter them out. Now, our solution is a robust FL framework. How does it work? As I said earlier, we've decided to combine PMAC and three-layer authentication. Specifically, we have multi-stage, which is device layer, external layer, and cloud traffic layer. And device layer is where the client's device are stored. We use graph score derived from L2 norms to filter out malicious clients. And then updates are sent to the external layer, which we use graph score filtering, robust local integration. And in the server layer, which is your own global layer, we use Jettison Shannon divergence and multi-step aggregation.
Okay, next we get to the experiments that after the R three-layer event. And the first one, we use data to data set. The first one is MNIST and CPAR10. And for model architecture, we use CMM for MNIST data set, and we use ResNet 18 to CPAR10. And for federation setup, we use total client of 5. Total communication route is 30, and for data set distribution, we use distribution. The first one is IID and non-IID data distribution with alpha 0.3 and 0.5. And for epoch, we use 5 total epoch per round. And for attack implementation detail, we use like static attack and 5 adaptive attack. For static attack, which means attacker strategy remain constant. Example given messaging attack, multi-ping, and gradient scaling. And for adaptive attack, this attack event detection by adapting behavior or mimicking benign client. Example given in adaptive gradient manipulation and minimizing distance backdoor. For our regulation, we use these 5 metrics. The first one is link accuracy, the second one is probability, the next one is surface rate, and the AUD, and FPM is 95% DPM. And this is example for our result because the experiment is for large. Because there is 10 types of attack and 6 types of baseline. So we use the one example. First one is emit on static attack. The baseline we got this, and this is the result on emit data set with adaptive attack. And this is the result on CPAC10 with static attack. And this is result on CPAC10 for adaptive attack. With that being said, the conclusion is that our architecture is highly effective in mitigating a wide range of attacks, such as static and dynamic attack, from a simple static method to advanced. The architecture successfully neutralized chaotic attack. Our primary goal is to counter sophisticated attacks. And the third one is the multi-layer approach is robust with each layer mechanism complementing the others to provide comprehensive security. For more in the future work, we hope to use more advanced detection method, hope to expanding our regulation to a larger scale data set, use complex data set with more complex models architecture, and not stop with the detection. We hope to attacker identification and update rejection so we can prevent and remediate attack. And in the future, we get the data sequencing mechanism to repair immediate damage after consulting. Thank you for your attention. My name is Diana Tanya and my friend
Ini di share screen juga tapi ya.
Jadi ini aja, nggak usah share. Hah? Nggak boleh buka nih. Oh.
Sabar.
Lah, kok keluar?
Belum dibuka. Ini yang
Berjalan.
kenapa? Ini ya.
Itu dari panel tadi. Ini ada tujuan nih. Kita lagi punya buat taruh kayak gini. Itu bagus ya. Iya kan? Iya kan. Oh, bulan Erik udah panik tuh. Gak tahu nih, mungkin jarang loh ini. Ini nggak ada gitu. Dari orang itu.
Executive pneumonia early is just about increasing diagnosis, one saving life. With me, Eric and Sam, let us take you on a journey through our research, comparing deep learning models for pneumonia detection. First, the outline of this presentation will include introduction, purpose of study, literature review, methodology, results and discussion, and lastly, the conclusions. Based on this data, back in 2024, we could see that pneumonia causes over 4 million deaths per year, which includes 502,000 children under 5. And its high mortality threatens public health and population growth, especially in low birth rate countries. And the problem with its challenge, where diagnosis relies on manual x-rays and manual review is slow and error-prone, where radiologists are scarce. And early and accurate detection is crucial to reduce its mortality rate. But why do we choose deep learning? Deep learning is over automated fast and scalable diagnosis, and its high performance in medical images classifications. Models like DenseNet and MVCNet are leading and architected in this domain. Okay, move on to the purpose of study. The purpose of study is to conduct fair comparative evaluations of two promising state-of-the-art deep learning models, such as DenseNet 121 and EfficientNet V2V3, and also to identify which architecture provides the best accuracy, robustness, and efficiency for automatic pneumonia detections. Move on to the literature review. First, we have CNN. CNN, based on numerous studies, proves that CNN models such as ResNet, Inceptions, EGG, DenseNet, and Efficient V2 are effective at learning complex patterns and extracting features from X-ray images automatically, and without manual feature engineering, which make them specifically designed for image analysis tasks, such as pneumonia detections, and is enable faster and more accurate pneumonia detection by learning unique visual patterns present in chest X-ray. Next, there is DenseNet 121, which is known for its dense connectivity, where each layer receives input from all previous layers, improving gradient flow and reducing vanishing gradients. And its low parameter make it lightweight and fast to converge. And lastly, we have EfficientNet V2V3. It's an advanced models use fuse and decon layer and compound scaling with squeeze and excitation as equal to achieve high accuracy and excellent feature extractions. Okay, thank you. So now let's talk about on how we do our research on the two different. First, the dataset. We use the publicly available Chester X-ray dataset from Mendeley that contains 5,863 pediatric chest X-ray images. It was automatically split into 5,000 images for training, 16 for validation, and 624 for test. And also the dataset provided a labeled image for classification of the places that is normal and pneumonia lungs. Next, move on to how we process our datasets to make it more suitable for our model training. First, for the FCNH V2B3, we resize the images to 300 times 300 pixels and we scale the pixel value between 0 and 1. Next, to the DensNet 121, we resize it to 224 times 224 and apply pre-process input, that is ImageNet normalization. Next, we also apply some kind of data augmentation method such as random flips, rotation, zoom, contrast adjustment, and also translation for making the model more nuanced. Next, plus weights applied for one models to balance it. And last, we use prefetch autotune to optimize the data loading and prevent I/O bottleneck. So here is our proposed model architecture. First, we implemented the both model, the DensNet 121 and also FCNF V2B3 with the processing pipeline that I explained before. And next, we use ADAM optimizer with learning rate of 0.001 and also fine-tuning learning rate of 10 to the power of -5. And for the training process, it was initially training with the base model frozen, followed by the specific fine-tuning layers. And also the DensNet 121 trained for 25 epochs, followed by 10 fine-tuning epochs. And for the FCNF V2B3 trained for 20 epochs and 15 fine-tuned epochs that results 55 epochs in total as maximum. And here is our results. On the training sets, DensNet 121 achieved 87% accuracy, 96% representation, 86% of recall, F1 score of 0.91, and AUC ROC of 0.95. It's quite promising, right? But let's take a look at the FCNF V2B3 performance. So FCNF V2B3 performance is outperformed all across the metrics from the DensNet 121. Achieving 96% of accuracy, 99% of precision, 96% of recall, 97% of F1 score, and also AUC RFC of 0.99. But the question is, will the FCNF V2B3 maintain a superior performance on the data? And on the data, the data shows that FCNF V2B3 still outperformed DensNet 121 across all metrics, that indicating that the model didn't experience any kind of underfitting or overfitting despite of the high performance on the training sets. So, on the training sets, then FCNF V2B3 outperformed the DensNet 121 across all metrics. And on the test set, FCNF V2B3 still outperformed the DensNet 121 in achieving 93% of accuracy, 93% of precision, 96% of recall, F1 score of 94%, and IUC/RC of 0.97. DensNet, on the other hand, achieved its best model in converse only just 8 epochs compared to 35 epochs on the FCNF V2B3. That makes the DensNet is potentially more suitable for low critical settings. But however, the DensNet 121 show a low recall, that which means the DensNet 121 could be missing in pneumonia detection of some cases, which makes the DensNet 121 is not suitable for clinical real application because the false negatives could not be tolerated. And plus, FCNF V2B3 outperforms the DensNet 121. That's likely because of the complex architecture of that allows more feature extraction and also attention mechanism resulting in better generalization. So based on the data, we can conclude the FCNF V2B3 is the most favorable state-of-the-art model for pneumonia detection, because the model successfully maintained the good balance between diagnostic accuracy and practical relevance in clinical application. Of course, in our research, we do have some limitations. First, the data set we use is relatively small and not fully diverse, that affect to the model's generalizability. And secondly, we had hardware limitations, we could then conduct the ensemble testing that maybe could affect to the improve performance. And next, for the future works, we or the next researcher could plan to use a larger and more diverse data sets and as well as testing it to the real world deployment in mobile or in a cloud clinical settings. And next, additionally, we aim to integrate the model explainability tools such as Galaxy AI to provide visual insights into the model's decision-making process. Last but not least, this isn't just talking about technology, it's about saving lives. Thank you.
Yung final ano, kung meron floating bawat
What if I told you that in the future? No, not with tarot cards or crystal balls, but with math. My name is Bennett, and with my research partner Matthew, we worked on a study called Evaluating Animosity in Medical Painters for time series based stock velocity. First thing first, why did we choose this topic specifically? Well, predicting stock prices can help investors spot trends, manage risk, and basically make better decisions. And as students, many of us are starting to think about our finances, right? I bet some of you guys have tried investing too. Well, stocks can be a really smart way to grow money, but only if you know what you're doing. The problem is stock data is messy. It's noisy, non-linear, and unpredictable. And some of them may behave differently. Some are fast, some are slow, and others remain stable. That's why we did our own research to see if time series stock forecasting can reliably predict stock prices in real world scenarios. We compared Animas and Hope Ventures to see how well each performs on different types of stocks. So let's get into it. We collected daily closing stock prices from Real Finance with Y1 package covering 2 to 5 years. Since Hope Ventures needs regular time intervals, we aligned VIPA to list of days using SRP and set the determined and use linear interpolation to fill in gaps like holidays. So the patterns were consistent for accurate forecasting. Now, how did we know if the stocks were slow moving, fast moving, or stable? We used 3 company tiers. The first one is RSI or Relative Strength Index. If the score was above 70%, we marked it as fast moving due to the strong momentum. Then we used Simple Moving Average 200, and if the price was within 2% of its 200-day average, It's likely slow-moving stocks. We also used 20 rolling day standard deviation to check its volatility. If the volatility was above 3%, we label it as fast moving. If it's under 1%, we label it as 1%. And if it's between 1 to 3%, we label it as fast moving. So by combining these indicators, we can label each stock accordingly before tossing the models and give us a balanced view of different factors. Now, before feeding the data into the models, we need to clean it and prepare it, right? So for Adam and Salma, we need to make sure that the data was stationary, meaning the mean and the variance stay constant over time. We tested that using the ADF test. If the data wasn't stationary, we then will apply derivatives. To check the models, we used ACF and PDCF plots to help us decide on the P, D, and Q parameters for Arima and also the seasonal parts of plot 7. As well winters, it needs regular time interval. So again, we'll indicate the resist days and set the frequency using linear interpolation, making sure everything was lined properly.
Let's go into model effect. Arima. It has three parameters. Q, which means price values, inversion for stability, and sales. Arima works well for stable or slow moving stocks. Second model is Arima. It extends Arima with several parameters. P, E, Q, and S to capture repeating cycles, making it better for mass moving stocks or cyclical stocks. Finally, the last model was Solvinter. We use the multiplicative version since the higher price often win larger swings. The model level, strength, and seasonality. Simple and fast, but less scalable with mesh data. So how we do the forecasting style? We split the data 80% for trading and 20% for trend testing. For Anima and Sanima, we use a step-by-step approach. Trade one day, trade in, then move to the next day up to 5 days ahead. For Holwinder is different. It gives all 5 days and earns using these states, but in the end, we compare the result to see which model performed well.
Now, once the models were trained, how do we know if they were any good? We used 4 evaluation metrics. First one is mean absolute error. It measures average size of prediction errors, plain and simple. Next, we have root mean square error. It gives more weight to large errors, and it highlights sensitivity to outliers. We also use mean square error, basically the RMSE before taking the square root, and it is also useful for comparing prediction accuracy. Last but not least, we use mean absolute percentage error, shows the error in percentage, which makes it more easier to interpret. Lower number on all of these mean metrics means better performance. Now, let's talk about the result, and here where it gets interesting. As slow moving stocks, both Arima and Sarima performed really well, with Sarima MAPE as low as 0.7%, but the best model is still dominated by Arima. Holwinters didn't stand a chance. One time its error was above 15%. Next one, we have stable moving stocks. Arima again dominated with MAPE score as low as 0.8. Sarima did just fine, but didn't outperform. So in cases where the seasonal patterns were strong enough, the simpler Arima model was just more efficient. Here in fast-moving stocks, Sarima started to shine. It managed to capture the cyclical volatility and gave us an AP score as low as 0.73. Holwinter, again, it just completely broke down. It couldn't handle the volatility and the noise of its data. So, what does this all mean?
Yes, Arima work best for stable or slow moving stocks. Simple model, simple patterns. But Sarima performs slightly better for fast moving stocks with seasonal or complex behavior. And finally, Holwinters, even the multiplicative one, gives higher errors, so it's like sweet for hotel prices. But there is some limitation in our research too. We only use closing price, no extra data like volume of news, and since Arima assume linear pattern, they can fully capture sudden or linear movements. So, what's next for the future works? First, we want to combine Arima and Sarima with deep learning like LSTM to balance statistic and nonlinear
learning. Second, you want to expand to multivariate forecasting by adding features such as trading volume, trading indicators, or new sentiment. Finally, we want to test this model on other markets like forex, commodities, or tech stocks to see if the results still hold.
In the end, our study shows that time series forecasting can support smarter, data-driven decisions in uncertain stock. Thank you for your attention.
I just want one I for in game. I for in
Good morning, everyone. So today I will present you about our research paper about evaluating CNN and fit architectures for impact detection. Before we begin, let us introduce to myself first. My name is Arjuna Randio and what my friend group is Arya Joko.
ya nanti macam lain dulu. Macam ini kita pencetak.
So we will talk about what can be fake news. First of all, define fake official interest manipulation, such as type manipulation, age manipulation, attributes manipulation, expression manipulation, and many more. As you can see in the image slide in the slide, we can see the original input image that has been deepfake manipulated to have eyeglasses, smiling expression, and older age. And the second one is voice and movements. Deepfake can generate one person image into fully realistic video, including the sound or lighting. As you can see in the original image, I prompted it to be say the word I love your example with the voice of an Englishman, make it aggressive and show it movements. As you will see in the next slide. I'm now showing the I will repeat it once. I'm now showing the even my necklace is moving to show this so unrealistically hard. Then we will talk about the rising threat of over 34,000 downloadable fake model variants were identified. These are the models that have been fine-tuned to produce fake images of identifiable people, including celebrities. 15 million types different generated methods have been downloaded across the internet since late 2022. As you can see, the rise of different videos from 2019 to 2023, there's so many total number of different incidents. Our main objectives have been divided into four sections. We compare performance of CNN and fit architectures for impact detection. The first one is systematic evaluation of both architectures using standard datasets. Second one is performance analysis across multiple methods such as accuracy, precision, F1 score, recall, and AUC. Then the third one is trade-off identification between precision and recall in impact detection. And lastly, application guidance for model selection based on use case requirements. Some of important middle work. The first one is Arijita 2023 with application of deep learning for image impact detector using convolutional neural network algorithm. The method uses in this research is standard conv to CNN architecture with convolution, pooling, and dense layers. The performance reached 90% average accuracy on large-scale datasets with 94.54% validation accuracy. The approach using basic CNN uses sparse categorical cross entropy and other optimization. And the significance, it demonstrates effectiveness of fundamental CNN principles for deepfake detection. The second related work is Arch et al. 2023 with unmasking deception, empowering deepfake detection with vision transformer network. The method used in this research is vision transformer architecture for deepfake detection. Then the focus is leveraging attention mechanisms for identifying manipulation patterns. The contribution, it demonstrates its capability in capturing global contextual information. Then lastly, the significance is part of broad trend toward transformer-based detection method. We use dataset shared self-built with 590 real images and over 5,639 fake images. As you can see, some of the examples of what is inside the self-built data. For the model architectures, we use FCNN video, approximately 12 million parameters. It approach local feature extraction, strengths on texture and edge detection. And the second one is vision transformer, approximately 36 million parameters, with global self-attention mechanism, strengths on long-range dependencies and global context. For the experimental setup, we use 70% training and 30% testing, and we use GPUs accelerated computing using Kaggle, and we process the image using image resizing, normalization, and augmentation. For the result, as you can see in the table, accuracy of efficient video reached 94%, which is more higher than vision transformer, which has 77%. And from our team, CNN is more higher than FIT, which means it's better for separating between real and fake images overall. CNN also faster, lighter, and uses fewer resources, which makes CNN is ideal for generating fake detection and real-time use. Meanwhile, FIT has higher recall and F1 score, which means it catches more absolute fits, especially subtle ones that might slip past other models. However, it is slower and more resource intensive. It's best for security critical situations where missing a fake is riskier than using more power. FCNet Zero is like a careful detective. It's highly precise, has fewer false alarms, but it might miss subtle cases. But vision transformer is like a paranoid safety dog. It has higher recall and catches more threats, but it has more false positives. For our future work, immediate recommendations. First, plan to cross dataset evaluation to test the models on unseen datasets to see how well they handle different impact generation techniques. Then also improve fine-tuning strategies for the fit, such as unfreezing more transformer blocks and adjusting learning rates for better adaptation. Another direction is exploring efficient variants from V1 to V7 find the right trade-off between speed and accuracy. For the advanced research directions, we aim to develop hybrid model through CNN fits integration, combining CNN strength in local detail detection with fits global context understanding. This approach will also focus on extracting insights and transform data and summarizing results effectively to support deeper analysis and decision making. In conclusion, we combine CNN and flip coding detection, uncovering a clear historical trade-off. The results guide model selection based on specific application goals, pave way for the future hybrid solutions. Thank you.
Morning, everyone. It's a pleasure to be here. My name is Juliana Panachanda with my research partner, Prince Gradioga, and we are both from Venus University. Today, we will be presenting our study titled Evaluating Feature Extraction Model for Extracting Semantic Information from Game Engine Documentation. And this research was conducted for INSEAD Data Conference. And, um, Before continuing to the explanation, let me start with a quick question. How many of you have ever felt confused or even frustrating when you reading through a long technical documentation? Now, imagine being an office game developer opening Unity or Garnet for the very first time. It's building the game, you find yourself lost in hundreds of complex instructions. This is the exact problem we wanted to address in our research. Actually, reading game engine documentation is often inefficient and time consuming. It slows down the game development process and flattens the learning curve. A major problem is that documentation highly unstructured and ambiguous in nature. And novice developers also lack familiarity with domain-specific conventions. We proposed a better solution that there is a critical need for an intelligent system to help developers comprehend information from the technical documentation efficiently. Here are the objectives of our research. We want to empirically compare the performance to identify a more efficient and systematic method to assist developers in comprehending technical documentation. Let's move on to the research methodology. First, we collected the data from the Unity, Library, Golden, and Engine documentation, stripped those data using a content product built with scraping framework in Python. The extracted raw text data then stored into a structured format and resulting around more than 20,000 entries. Okay, let's start with the data processing. Actually, we want to cleaning the data. We want to remove the null values, duplicated, and also lowercase the string types to adjust the to adjust all of our entries in highly for the string types.
So moving on to the second step of data pre-processing, which is data integration. So we can see first we combine the column title and first column data into one table. Then we standardize the column name to create a new column named main section, game engine, and label to create a more structured table. And then the third one, we use the concat function from the pandas framework to merge those standardized data frames. All of these actions causes uh, the table to produce a more structured manner. So the model can read the table more easily. Then moving on to the third data preprocessing, which is normalization and encoding. First, we apply stopwatch removal, which enhance features quality, reducing noise, and focusing on more meaningful terms. What that means is we simply just remove some of words that are simple but uninformative. Then we apply lemmatization. Lemmatization converting words to their dictionary-based forms, combining different words variations into a single feature. Then we apply label encoding. The label column was converted into a numerical format using label encoding to prepare the data for model training. So all the data
and merge allows CNN to do what they do best, automation extraction, while letting transformer handle global context. Here for our data set, we use two data set for Kaggle. For flash share classification, we use a data set that consists of 5,000 image categorized into five classes: hard, oblong, oval, round, and square. And for the facial expression recognition, we use FER dataset with over 35,000 grayscale image across different emotions such as happy, angry, and sad. So after gathering all the data that we need, we are moving on to the next step, which is pre-processing. So there's three steps of our pre-processing. First is data cleansing. We clean the data, so some images are corrupted, and then we remove those data by using automatic scripts. This is prevalent in the face shape data set. The next step is face cropping using Hard Cascade, which is a library from some people. So it will crop the image to focus only on the facial region. This is again, this is again, is done on the face shape data set. And the next is image transformation, such as resizing, normalization, and other augmentation techniques like rotations, flips, and perspective adjustment. All of these are done to improve the quality of the data sets, and again, to make the model performs better across the data sets. The next step is hyperparameter optimization. We use the Optima framework for this task. Our main goal is to maximize the macro at one score, which balances performance across all classes, even those with fewer samples. For example, in the FER 2015, there are one class that is really low in data, which is around identity image compared to its peers, which is around thousands. We took parameters such as learning rate, dropout rate, weight decay, bed size, toilet smoothing, and gradient preview. Its trial ran only for 15 epoch, with early stopping to avoid overfitting. And after all of that, we got our result. And now we will discuss those results. So the FER 2013 or face expression data set only achieves 0% development score, while the face shape data set only achieve around 0.78 F1 score. While this result actually appears promising at first, we observe severe overfitting when training those models. The model consistently perform much better on training data set. We are here seeing difference around 0.18. So the training data set consistently get 0.9 plus F1 score, while our testing data set only get around 0.7. This reveals actually a fundamental mismatch. The model's complexity, which is over 86 million parameters, was far too large for our relatively small data sets.
Double click up.
Windows and the order and the scroll is on the panel. Cyberbullying has become a threat with serious consequences.
Hi
Hi
everyone,
everyone, my name is Raja Khalid
and I'm here with my partner Excellent. We are here to present about our research paper regarding deep learning for detecting cyberbullying in social media. Here is our outline for today. Okay, as of February 2025, there are 5.24 billion social media users. That means most people have used social media to interact with other people online. Uh, furthermore, a study conducted since 2007 until 2023 on several schools showed that on average, 31.2% of students have experienced cyberbullying. This becomes worse from the fact that since 2016, the rates of cyberbullying have actually increased from 33.6% all the way to 54.6%. That's why many researchers have performed a study regarding how to mitigate this issue. They have used several artificial intelligence techniques and have found out that deep learning can outperform many traditional machine learning in this domain. That's why we conducted this research in order to find the best deep learning method to predict and mitigate this issue.
The main goal of our research is to develop automated systems that can detect cyberbullying in social media using deep learning techniques. We aim to compare the performance of three model estimators. First, CNN, PL0, and combining both CNN and PL0. This leads us to our research question. Which deep learning model is the most effective to detect cyberbullying in social media based on trade data? By answering this question, we hope to identify the effective and accurate model that can implement in real-world modernization system. To understand our approach, let's look at some of the key concepts. First, cyberbullying refers to bullying or harassment conducted through digital platforms, often anonymously. Then we use CNN or convolutional neural network, which is effective at detecting local matter such as specific keyword or phrase. Then we have PLDM, which process text in both forward and backward direction, allowing it to capture spatial context from the input text. Then we have our hybrid models and PLDM that combine these two strengths. Capturing both sequential, spatial, and contextual features from the input. For feature extraction, we use this flavor, a lightweight transformer model that provides contextual word embedding. Additionally, we use vector rule-based sentiment tools that is particularly suitable for informal language like Twig.
So we took our dataset from Kaggle consisting of 47,000 tweets, which we will later use to train our model. First, we perform pre-processing, which consists of text normalization, emoji and software removal, oversampling, and many other pre-processing methods to ensure that our model is able to are capable of generalizing our text data. And then we perform feature extraction using Distilbert to extract contextual embeddings and Fader to extract sentiment scores, which can be positive, neutral, or negative. And then we train our model, which consists of CNN by LSTM and the hybrid model CNN by LSTM, and perform hyperparameter tuning on them using grid search to find the best parameter for hidden layer, dropout rates, and learning rates. Finally, we use our test data to evaluate each model using the following evaluation metrics. Out of our data set, we took 80% of the data to train our model. And then we use 20% of the data to test our model and evaluate their performance on accuracy, precision, recall, and advanced score. From our results, we found that the hybrid model, CNN by LSTM, performed the best out of all three models across all four accuracy, all four metrics, managing to achieve a score above 94% across all four metrics. However, it has to be noted that the hybrid model requires a large computational resource. This can become a major consideration, especially since the hybrid model only offers a 0.5% increase when compared to the individual by LSTM model.
To conclude, all three deep learning models demonstrate strong performance, each achieving over 93% accuracy. Among them, the hybrid CNN-PLSTM model proved to be the most effective, consistently outperforming the other across all evaluation metrics. The use of Distilbert and Fader also contributed significantly to improving classification performance by enriching the input features with contextual and emotional information. However, we also observed that the hybrid model demands more computational resource, so it makes less ideal for real-time deployment under resource constraints. As we remark, we propose integrating this approach into real-time monitoring system, enabling social media platforms to detect and moderate harmful content more efficiently and promptly.
All right, that's all for our presentation. Thank you for your attention.
Good morning, everyone. Imagine calling a thousand of IMDb reviews, some pricing a movie, some critical output. So, sentiment analysis can help to classify the review automatically. But with models, CM and web, but the model like black box hard to understand. That's why this study, using explainable AI, help to reveal how it should make the prediction. Before we get into the detail of our research story, let's us introduce the team behind. I am Priscilla Fiona and my research partner Natasha Fernandez. Okay, movie review on platform like IMDb play an important role of audience or for film industry. Sentiment analysis with NLP can help to classify review as a positive or negative with NLP. The STM angle are effective, but the black box make the decision making hard to understand. So explainable AI, sharp and line help to reveal how each word can make the prediction, and this is a study compare not only in quality of classification but also in how to word make the produce with IMDb review. Many studies have shown the success of deep learning method in sentiment analysis, such as LCM with FastTech, with achieved 86% accuracy on the IMDb dataset. Transform-based models such as DeepBird have also been shown to improve accuracy compared to standard BERT, especially on small training data. To improve the transparency of black box model, explainable AI techniques such as Lime and Sharp are weekly used in various domains, from text analysis to medical and credit prediction. The result of the study show the Sharp generally provide more stable, accurate, and spread explanation than Lime. However, research that directly compare Lime and Sharp on the IMDb dataset with faithfulness metric is still limited, which is the focus of this study. To answer our business questions, so we follow this methodological flow. First, we collect and clean the data set. Then we try two models, LSTM and BERT. Then we evaluate both models. And for explain each predictions, we use XAI methods like Lime and Sharp. And then we evaluate it quantitatively and qualitatively. And then we compare and analyze the result. So we use an industry standard data set that is IMDb data set contains 50,000 rows. So before the data could be processed, there is some pre-processing steps that could be conducted. The first one is cleaning like HTML tags, etc. And then tokenization in order to change the format, the text into a machine readable format. Then we do the predict. And then we build and try to classify our text classifier models, that is by LSTM or by directional long-short-term memory. It is a known model for its capability, for its word processing. And then for BERT, it is a state-of-the-art model that is capable and known for its good and superior understanding of complex context review like movie reviews. And then we also use pre-trained glove embeddings. We followed by LSTM and a robot layer to reduce overfitting. And for BERT, we also use a learning train scheduler and a pre-trained BERT-based case model to ensure effective training process. And then next, despite their high accuracy like BERT, Border cyber are black boxes, so we don't know why a prediction is made. So that's why we need to use XAI methods, that is Lime and Sharp. Lime predicts, explain the prediction locally by looking at neighboring words, while Sharp, it is more holistic. They use game theory, Shapley values, and then they measure the contribution of each word in the prediction. And then next, for evaluation, for the models, text classifier models, we use some standard metrics like accuracy, precision, F1 score, and recall. Meanwhile, for XAI, like Lime and Sharp, we use qualitatively and quantitatively. Then for quantitative, we use faithfulness metric. Specifically, it is prediction gap on important observation and unimportant observation, or in abbreviation, that is PGI and PGU. And then for our first result in text classifier model, we can see that bird, as expected, the bird beats LSTM by LSTM in all metrics. Like accuracy, we can see it is 91.62%. In comparison of LSTM, it's only 80%. And we can also see in the conversion metric, BERT makes far fewer prediction errors. It confirms their high accuracy and high capability. And for AI, well, first we conduct the qualitative. We can see here, this is on the screen, it is the same negative review, and it's reviewed by Lime and by LSTM and BERT. Well, we can see they both negative, but BERT had more confidence. It is an absolute one prediction probabilities. Like push words like ways, awful, the silence words are negative. You can see, but for BERT it is more confident. And we also conducted same analysis using SHARP, but due to no time, so the full details are available on our paper, with SHARP provide a more holistic view. For quantitative, we see a pretty interesting finding in PGI score. You can see that Lime always beat SHARP in terms of PGI. Why is it? Because their different working principle. Lime, working by locally looking at memory words, they focus on more excellent keywords, while SHARP, it is more measure more words more holistically. They distribute the importance of words more hot or across more features. So that's why Lime always higher. And also in SHARP, especially on BERT, they also work on token level. So that's why sometimes the feature is include a subword or subgroup word. That's why sometimes SHARP is lower. So what does all this mean? This means that Lime is more effective for finding the most extreme keywords, while SHARP provides a more holistic overview. So our key finding, quantitatively comparing Lime and SHARP is not straightforward. So that's why we need to use maybe another metrics to compare both of them quantitatively. So the conclusion, the study compares sentiment classification model RSTM and BERT with expanded Blair method, Lime and SHARP on 25,000 IMDb test data. BERT achieved the highest perform with 91.62% accuracy. Lime was effective in identifying feature with the most extreme impact, while SHARP provides a more holistic explanation. The quantitative score difference are not only due to technical challenges such as unit displacement, but also SHARP inherent property of evenly distributing influence. A key limitation is the use of a single dataset, so feature research should explore more diverse dataset and develop token level explainable AI evaluation metric. That's all from us. Thank you for attention.
have a very strong earth-based connection.
In recent decades, the frequency of natural disasters has increased significantly, causing major losses, including casualties, long-term environmental damage, and economic impacts. This situation demands a more responsive and adaptive information system to support disaster management. However, traditional information channels often fail to deliver timely and accurate updates. This is where social media platforms like X play a crucial role. With an average of 6,000 posts per second, social media becomes a highly potential source of real-time information. Unfortunately, social media data is highly unstructured and ambiguous. Many posts are incomplete, irrelevant, or difficult to process it manually. Therefore, an intelligent AI-based approach is needed, one that not only classifies the type of disasters, but also extract the location information in real time. I'm Shirley Margareta, and together with my partner, Noviana Renovinasi, we present our research which aims to address these challenges.
The objective of this research are develop a different type classification model for social media posts using FFNN and CNN, which enables the system to recognize the different types of disasters quickly and accurately. Then, we build a disaster implementation extension to name entity recognition, which utilizes real PM and web to contextual location information from short and informal text. The level is analyzed and compare the performance of models across classification and extraction data to determine the most effective model for handling short, ambiguous, unstructured, informal social media text. In this research, we apply for deep learning model, which is widely used in text processing. For the data classification model, we use the forward neural network. This is the This is because FFLE able to focus on global keywords, which are the often dominant indicator in short and unstructured text query. In some formalization expression, DLCF reached an equal score of 88%, while third reached 86%. This shows that DLCF works slightly better because it can understand the order of work and capture location names more accurately. This result also the fact that DLCF when combined with system and is an effective strategy for handling missing and unstructured text from social media. It's also our presentation review. Good morning, everyone. Today we will present our presentations titled A Satellite Guided Deep Learning Approach for Proactive Forest Fire Detection. We actually submitted our journal on ICITBA, International Conference on Information Technology and Digital Applications. But before we start the presentation, I would like to introduce our team. First, I'm Naomi Ida Natasha, and with my partner, and for Olivia Chanda. First, we talk about the background. Why do we choose our topic as our journal's topic? Forest fires more frequent and more severity. What are the causes? You can guess, as you guys can see on the screen, that the global temperatures rise and then human activities like farming, land burning, agriculture, and so on. The key fact, according to the NICC data, that 350 million hectares are burned annually worldwide, and 2018 until 2022. What is the problem? The problem is that traditional methods such as ground patrols and satellite terming imagery are slow and have limited coverage. So what are the plans? What is our plan to do next? That research shows that satellite imagery and artificial intelligence, if we combine the two models like that, will provide a faster early detection. Is it true? We don't know. We try to do the research in this journal. So what are the problems before? If you guys using CNN alone or SPM alone, CNN can overfit and miss large patterns, while SPM cannot handle raw imagery data effectively. So this is like the problem. We took the data from satellite and then we process the data by CNN and then we classify the data by SPM and then we map the data. So we knew that where are the fires and what are our goals. First one, we will develop hybrid model. We will combine CNN and SPM. The second one will use Sentinel-2 multispectral imagery, and then the third one will integrate temperature, humidity, MDVI, and TNVR. The fourth one will detect burn and unburned areas accurately. The last one will enable faster wildfire early warning. And the methodology related works and results will explained by my partner.
And let's move to the methodology. So our data set comes from Sentinel-2 multispectral imagery, and we're using RGB, NBR, SWIR1, and SWIR2 for our bands. We level the burn areas based on the difference normalized burn ratio with 0.1 threshold following the K and Benson method. So in the process, first we do the velocity data with atmospheric correction and resetting the bands to 10 resolutions, also computing the NBR, DBR, and I. And we perform the feature sections by modifying the resolution for CNN with multi-scale kernels to capture the fire patterns. And we use SPM with ambient kernel for the classifications to separate the burn and unburned path. And we also do the provisions for accuracy, precision, recall, and transform IOU, AED, and we also test the models in different location to check the precision. And we also review several words like FireNet, with high simulation accuracy, but less on focus classification. There are also YOLO-based models with strong and fast for smoke detection, but reliably on the high quality data. And EmissionNet V0 and UNet that gives good results, but we can across topics adaptively. So our approach, CNN and SBM, combines the deep learning and machine learning with the environmental data for member classes. So more result, we got 0.95 accuracy, and for the burn area, we got 0.87 for the precision, 0.98 for the recall, 0.92 for the advanced form, and for the upburn area, we got 0.99 for the precision, 0.93 for the recall, and 0.96 for the advanced.
Okay, based on what for explanation before, we took this as our conclusions. These are the conclusions. The first one, if we combine CNN and SPM, it's better than if we use CNN alone or SPM alone. And the model, I mean, if you guys will combine the CNN and SPM, works well on imbalanced data sets and high potentials for only wildfire detections. It also can help authorities respond faster. And then that's not the end of our project. We hope that something could get better in the future. So this is our plan for next. The first one will expand the data sets to multi-reactors and multi-climate. The second one will use time series data for fire progressions over days. We will use UAV and IoT sensor integrations. Last but not least, we hope someday we could develop lightweight models for real device. And then okay, that's all. This is the summary. The first one, if you guys combine CNN and SPM and the model works together with satellite imagery, we will get accurate, reliable, scalable wildfire detections. It also supports faster disaster prevention and ready for operational implementations. If you guys have any questions, better ask after these presentations. Thank you so much.
Tes, tes. Kedengaran nggak ya? Tes, tes. Halo, 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 halo. Tes, 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 tes. Tes, tes, tes. Tes, tes, tes. Tes, tes. Tes, 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 tes. Thank you. Good morning, ladies and gents. My name is Ian Mati Shombing, and today I will be presenting our research on hyperparameter tuning in Bitcoin price prediction models. This research evaluates the effectiveness of genetic algorithms and Bayesian optimization for optimizing gradient boosting models, specifically focusing on Bitcoin price prediction. This work was done in collaboration with my co-authors, Mr. Christopher Kiswartono, Mr. Ivan Sebastian Albert, and Mrs. Diana, and is being presented at the Gen City International Conference in Bali, December 2025. As we all know, Bitcoin is notorious for its extremely high price volatility, making price prediction a major challenge. With the increasing number of investors entering the cryptocurrency market, it is crucial to have accurate prediction models. Our research aims to evaluate and compare the performance of two optimization techniques, genetic algorithm and Bayesian optimization, for improving the accuracy of gradient boosting models in predicting Bitcoin prices. Bitcoin's high volatility creates significant challenge for price forecasting, especially when compared to traditional assets. Several methods have been used to predict Bitcoin prices, such as deep learning models like CNN and LSTM, and ensemble models like Random Forest, XGBoost, and LikeGBM. However, the hyperparameter tuning of these models remains essential to improve their performance and accuracy in this volatile market. The main objective of our research is to compare the effectiveness of genetic algorithm and Bayesian optimization. in optimizing the hyperparameters of gradient boosting models, specifically XGBoost and LagGBM. To predict Bitcoin prices, our goal is to assess which of these techniques yields the most accurate and reliable prediction for such volatile data. Master learning models, including XGBoost and LagGBM for Bitcoin price prediction. These studies have also focused on hyperparameter optimization methods such as grid search, random search, and more advanced techniques like genetic and Bayesian optimization. Our research builds on these approaches to evaluate the potential GINDO in improving gradient boosting models. For our research, we utilize Bitcoin price data with 4-hour intervals from the TradingView website. Spanning from January 4 to early 2025, the data contains 20,556 entries with 25, including opening, high, low, and closing prices, as well as technical indicators like EMA, MA200, volume MA, and RSI. These features provide a comprehensive dataset for training our models and evaluating the impact of hyperparameter optimizations. Before training the models, we perform filter selection using the Boruto algorithm. Boruto is a random forest-based method that compares the importance of original features with shadow features. It identifies the most relevant features and eliminates less important ones, which improve the model's ability to focus on the most significant factors affecting Bitcoin price prediction. For our gradient boosting models, we use LagGBM, which is a decision tree-based algorithm optimized for speed and memory. LagGBM convert continuous features into Kabin histograms using gradient-based one-shot sampling or GOSS and exclusive feature bundling or EFB to improve computational efficiency. The model's leafwise growth strategy minimizes overfitting, while the objective function is reduced using gradient and Hessian during iteration, ensuring a fast and accurate prediction process. We also employed XGBoost, another decision tree-based algorithm known for its deep optimization. XGBoost uses regularization, which is L1 and L2, to avoid overfitting, and the string edge method refines parameters during its iteration. The use of approximate tree learning further optimizes the decision tree creation process, making it highly effective for predicting Bitcoin prices in a dynamic market. The genetic algorithm was used to explore a broader parameter space through selection, crossover, and mutation process. Selection chooses the best individuals based on performance, while crossover creates new individuals by combining characteristics. Mutation introduces randomness to explore a larger solution spaces, minimal traps. GI's ability to handle complex makes it an ideal choice for Bitcoin. On the other hand, Bayesian optimization uses a gradient process as a predictive model to optimize hyperparameters. The goal of BO is to balance exploration of less known areas with exploitation of already known regions to find the optimal solution. BO is technically efficient to find optimal solution with proper iteration conventional methods like grid or random search. And it's suitable for optimizing hyperparameter in complex model like XGBoost and LagGBM. Next will be explained followed by the conductor.
As for the result, in our first data set, we evaluate its model's performance based on prediction accuracy and error metrics. The results show clear performance boost when hyperparameters were 2 BTA, especially in volatile price factors. The next in the using dataset 2, In our second data set, a more refined feature set, GA once again outperformed Vivo, showing better generalization and stability in prediction, even with noisy data. Our findings show that GA provides superior result for Bitcoin price prediction compared to Vivo, particularly in the context of cryptocurrency's unpredictable nature. For future worlds, we suggest adding alternative features such as structural media sentiment or news data, and extending the study of to deep learning and hybrid models. One limitation we faced was computational costs, both in terms of training time and memory usage. Thank you for exploring Bitcoin price prediction with us. We hope this presentation has given you an understanding of how hyperparameter optimization can enhance prediction models. Thank you.
Good morning, everyone. I'm Asha Rabda Spangani.
And I'm Stefan Aris. Today we will present our research title is Comparative Analysis of AS and RSA in Security Communication. This study was conducted together with our colleagues at the School of the Computer Science, Bina Nusantara University.
Before we start, does everyone knows about WhatsApp or maybe email? Well, every time we send a message through those apps such as WhatsApp or email, the text doesn't travel in its real form. Instead, it's first encrypted in the script text. Then the intended recipient encrypted it back into the plain text. Well, in today's digital age, this process was known as cryptography, which is essential for protecting sensitive information such as personal chat, financial data, or official documents. Two of the most widely used algorithms for cryptography are AES and RSA. AES is a symmetric algorithm that uses the same key for both encryption and decryption data. Meanwhile, for RSA is an asymmetric algorithm that uses public key for encrypted data, that is the private key to decrypt data. However, there's always been a trade-off between performance and security. The trade-off between performance and security is what made us do these comparative studies between AES and RSA for choosing which one is the best algorithm for securing digital communication.
Our research had the three main objectives. The first one, to compare the computational performance of AS256 and RSA 2048. And the second one, to evaluate them based on the key generation, encryption and decryption speed, and the memory usage. And the last one, to identify which algorithm is more suitable for the application and which is better for the secure extent.
Moving on to related works, well, several previous studies have studied this algorithm, instance such as Verma and Sharma that analyze the influential effect in AES and RSA, that Jean Charles and Bianvik that explore the hybrid crypto system. And on the other hand, there are Yewol and Okori that emphasize the RSA's role in cloud security. And last, there are Channel et al. That identify that AS that identified AS in speed and bulk encryption. Well, from this line of works, well, AS is already been the de facto standard in many government and commercial applications. While on the other side, RSA is dependable in securing communicate in security exchange. From these studies, we saw that there is no single winner, which is why we designed an experimental comparison of AS256 and RSA2048.
Imagine yourself in secret message to yourself. The big question is, how do we measure which encryption algorithm protect it better? To answer this, we built the simple client-server model. The client encrypt the message before sending, and once the server receives it, the message is decrypted. We implement both AS and RSA separately so we could compare them under the same condition. Our evaluation focus on three key aspects. The first one, key generation time. How long it takes to create the encryption key, and the second one, encryption and decryption speed. How quickly data can be processed. And the last one, the memory usage. How much system resources are consumed. To make the test realistic, we use the text file of different size like 1 kilobyte, 20 kilobyte, and 50 kilobyte. And this allow to observe how each algorithm behave with both small and larger data. For this experiment, we chose AS256 because it represents strong symmetric security, and RSA 2048 as the standard asymmetric benchmark widely used in the secure communication.
Consider we tested. Then there are three metrics that we have: key generation, decryption speed, and memory usage. Well, the results doesn't quite shockingly because if we check it in the key generation time, we'll find that AS only took around 0.03 milliseconds to generate the key. Meanwhile, for RSA, it took between 500 to 2300 milliseconds. Moving on to encryption decryption speed. In encryption speed, AS was still remain efficient with it took around 3 milliseconds, while for RSA, it took sometimes over 10 seconds. Moving on to decryption speed, well, AS become much faster because it only took around 0.4 milliseconds. Meanwhile, for RSA, it took between 150 to 1700 milliseconds. And one, in memory usage, AS was lightweight, meanwhile RSA consumed much more. And that is proof that RSA is quite hard. Well, especially while RSA consume much more, especially as file size grew, which make it less suitable for encrypting larger files. So overall, AS excels in speed and efficiency, while RSA is more suitable for secure key distribution rather than both data encryption.
AS is better in speed and efficiency, while RSA is good for secure distribution. Since AS is much faster, efficient, and consistent in using memory, AS is highly suitable for a real-time system such as IoT, VPN, and POID. On the other hand, RSA is slower and consume more memory, but it excels in secure key exchange and authentication, which is why it remains a critical part of the modern cryptography. Looking ahead, we plan to design a hybrid AS and RSA encryption model because combining the speed of AS with the secure key management of RSA. In addition, we aim to expand our experience to cover different data types in real-world environment and explore language alternatives such as elliptic curve cryptography for computer secure communication.
Well, Thomas, thank you for your attention.
Untuk booking sih untuk sebelum diambil orang.
Okay, good morning everyone. Today I'm excited to
Yang
present
penting
our
tapi lihat
research
dulu
on
asik.
comparison of machine learning and
Iya,
deep learning models
Nanti
performance in
kalian
classified music
takutnya di
genres.
pojok.
A critical challenge in today's era of
Siapa tahu
digital
ada yang
music
lebih enak kalau
overload.
di sana.
Before that, let me introduce myself and my partner. My name is
Kamu
Calvin
lebih blok
Sitosan,
gitu.
and my partner is Dr. Sugiyotaro from
Janjian
Nusantara University.
minta visit.
So for the presentation outline here, starting with introduction, then try to review methodology, result, and finally the conclusion. So first of all, the introduction. What is the importance of music in society? Music is a universal language that transcends cultural boundaries. Beyond entertainment, music serves as a medium for emotional expression, stress relief, and model and mood enhancement. With that importance of music, no wonder there are over 100,000 songs released daily, according to Billboard, making manual genre classification impractical. So there is a need for automated genre classification. Why? Because platforms like Spotify and YouTube Music use music recommendation systems that rely on accurate genre tagging to improve their recommendation systems accuracy also. There is also a need for organization of digital music libraries and user experience on streaming platforms. Manual labeling is no longer feasible, and this is where machine learning steps in. Traditional machine learning models such as SVM, Random XGBoost, and TNN use manually extracted features from the song to identify the gender. And on the other hand, deep learning models such as CNN process spectrograms to improve more automatic classification. Despite the advancement of machine learning and deep learning, several challenges persist. First of all, overlapping features such as drums in rock and metal can cause misclassification. Next, the balancing accuracy and computational efficiency is also difficult because high accuracy models may be slow for real-time use. Because of that, in this research, we are doing comparative analysis of SVM, Random Forest, XGBoost, KNN, and deep learning model CNN on the GDSN dataset. We are doing reprocessing dataset, then hyperparameter tuning via randomized search. And finally, we are doing the performance comparison, but on accuracy of efficiency of each model. The goal is to find out which model is the best that balance the accuracy, efficiency, and scalability for real-world music classification applications.
And we move on to the current review, the first model, and after we did some of the review, it gives us more model. The first one is SVM. The boost accuracy was splitting songs into 4 bits interval, while GD is set here in 93% accuracy with RCC and only 70% of level score. It's suggesting a probability. The second one is Random Forest. Random Forest is a lightweight, fast, and repeatable model that is already in the 2022 report that 77% accuracy with RCCs and SU and 2022 reached 80.3% by segmenting into 3 segments. It's showing how reversing is successful. The third model is XGBoost. XGBoost is a strong gradient boosting model. You must have all and 2023 achieved 91.79% accuracy with MRCCs and spectral contrast, while Simon and Tristan at 2022 reached 81.94% through today. The fourth model is KNN or KNN network is classifies music by similarity, but it's slow at prediction. Around 50-second samples with 10K yield only at 43% accuracy But when it's secondary
Mau
to
toko mana?
second quiz,
Balik
it
udah.
boosts accuracy to
Di sini sama ongkos nih.
92.69%. Last but not least is the deep learning model,
Tapi
CNN. CNN learn time frequent patterns from spectrogram, achieving state-of-the-art of the result. D et al. At 2023 enhanced performance with CNN, and at 2022, Chen et al. Introduced a CNN transformer hybrid that improved both accuracy and speed. To the powerful results, the CNN required large dataset and through high computational efficiency.
Moving on to the methodology, we use the GTSET dataset, a well-known dataset for music genre classification. It contains of 1,000 audio tracks, each 30 seconds long, across 10 genres. It has 58 expected audio features like MPCCs, chroma STFT, and so on. For the pre-processing, we split the data into 3-second segments to increase the data volume. We are doing data pre-processing. The first one is data cleaning, where we handle missing values, duplicate data,
beda
and
2 kilometer
columns.
pula.
After that, feature engineering. First one is label encoding, where we convert general labels to numerical values and standard scalar to submeters. After that, we are doing data splitting, 80-20 ratio, training to testing for unbiased evaluation. After that, we are doing feature scaling again to apply standard scalar post splitting to ensure uniform feature scales. For the model training and hyperparameter tuning, here are our configuration. The first model is FVM, where we use RBF kernel, and here is the key parameters. And for the hyperparameter tuning, we are using random methods for exploring the C parameter, gamma parameter, and kernel type parameter. All that going through 5-fold cross validation tested in 20 combination. Next, the random forest, where we use a sample of 200 decision trees with max depth of 20, and for the hyperparameter tuning, we explore the tree count, depth, and split rules. Next, the XGBoost, where it boosts weak trees irreducibly per testing sequential samples. Here are the key parameters, and we also optimize the trees number, depth, and loading rate. Next, the TNN model, where we use Euclidean distance with 10 neighbors. For the hyperparametric tuning, we tested neighbors number and distance metrics. Next, the CNN, where we use 3 convolutional layers, and for our regularization, we use Westrom group out of 0.3 and max pooling with a total of 2. For the training, we use the Adam optimizer with 50 epochs and rate size of 32. And finally, for our evaluation metrics, we are going to evaluate the performance metrics such as accuracy, precision, recall, and flow score, computational efficiency, which are ready or prediction time, both pre and post hyperparameter tuning, and feature importance, where we identify key audio features influencing genre classification. Here are our results. As we can see here, SVM is the highest accuracy model at 93.14%, and XGBoost is the fastest model with the fastest prediction time. Key observation here is that SVM showed potential overfitting due to high test accuracy by chance. And after that, CNN delivered strong performance despite conditional demands, and XGBoost offered the best speed accuracy trade-off. After doing hyperparameter tuning, here are our results. The new improvement here can achieve new highest accuracy at 93.94%, number 2 XGBoost, 92.39%, followed by CNN and SVM that dropped to 90.49% because the tuning improved general stability but at cost of accuracy. After that, the random forest still the least accurate. The critical insight here is that XGBoost emerged as the most reliable for real-time applications due to its consistent high accuracy and speed. Final recommendation here, the best overall model is XGBoost. The other option is KNN and CNN. Next, moving on to top 10 feature importance. As you can see here, the most important feature is perceptual variance, where it has a role to capture variation in loudness and tremble characteristic perceived by human. The impact that it consistently ranks first across all models, indicating its universal predictive power. For the example, it can distinguish the classical and electronic genre. Other critical features here are spectral bandwidth mean and so on. Key observation here is that the consistency that it were stable across tuned and untuned models, confirming these features are inherently informative. For the other interpretability here, the spectral features can differentiate genres by instrumentation, chroma features can identify harmonic patterns, and perceptual variance can track human-like perception shift. Okay, the conclusion, the model performance, the best one that we found is KNN, achieved the highest accuracy at 93%, but it has a slow time prediction. So we choose another one is XGBoost, which provide the best balance with 92 and 30.39% accuracy and the fastest speed, making it ideal for real-time use. For the critical feature insight, we found that perceptual volumes is emerged as the most discriminating feature, effectively capturing loudness and timbre that makes to several genres such as classical and electronic. Limitation, here is the limitation, the free time Google Colab, here is us future prediction. That's all for our presentation. Thank you for listening.
Backend framework are essential in modern software development. They handle database management, business logic, and directly influence performance and scalability. However, many developers struggle with choosing the right framework. For instance, Laravel is very popular because of its rich feature, but it tends to be slower under heavy load. Backend framework are essential in modern software development. This raises our main research question. Which backend framework perform better in terms of scalability, stability, and speed under standardized testing conditions? Here's the outline of our presentation. We will start with the results that have been asked, followed by introduction, study literature, methodology, result, discussion, conclusion, and finally our recommendation. The backend is the foundation of every application. It manages data flow, user requests, and core logic. With the rapid growth of digital application and a larger user base, the demand for robust and scalable frameworks kept increasing. Previous research on backend framework had several limitations. Many did not use standardized testing environment. Some covered only on a limited number of frameworks. Must focus only on speed and ignoring stability. Our study addresses these gaps by conducting a fair, consistent comparison across 5 popular frameworks like Django, Express.js, Kim, Laravel, and Spring Boot. We use Apache JMeter for testing and Docker for behavior. From prior studies, we found that Laravel and Django are feature-rich and have strong ecosystem, but they are slower under stress. Express.js and Go-based framework like Gin show excellent performance and scalability. Spring Boot is widely used in enterprise systems because of its reliability and microservice support. Additionally, non-technical factors such as documentary quality, ecosystem maturity, and developer experience play a critical role in framework adoption. This shows that performance alone is not enough. The overall developer experience also matters.
Now, let me explain our methodology. First, we deployed all frameworks run on isolated environment on Dockers. And then secondly, we load the tests using Apache JMeter. We run it on the hardware on Intel Core i7 1260p with 60 GB of RAM and Windows 11 Home. Now, for the research object, we use a simple news API endpoint. There are four of them, namely hello news /items and /search using MySQL database with standardized JSON format. For the experiment setup, to simulate real-world usage, we use 250 concurrent users with a 30 seconds RAM uptime and random controller to simulate real user behavior. There are three metrics measured in this research. There are throughput, response time, and error rate. Now, let's see the equation behind the throughput and error rate. This is the result of the throughput. In terms of throughput, as you can see on the graph, Gin and Express.js has the higher throughput. This means that these two frameworks can handle many concurrent requests. For the others, like Django, Laravel, and Spring Boot, the results are lower. They have lower throughput, and this means they can deliver like moderate throughput with stable performance, but it's not as high as Express and Django. Now, Django and Laravel reported the lowest throughput here, highlighting the limitation under heavy workloads. Now, when we measured our average response time, Gin consistently delivered the fastest response time with minimal latency. Express.js also follow a second that performed well, maintaining low response time. Also, Spring Boot showed moderate results. Django and Laravel, however, had the highest response time. Especially Django here, as you can see, Django has the highest average response time. This is because of the higher error rate that Django suffered during the test due to higher workloads. Now, as you can see, Django has the highest error rate here. Now, the other framework maintain around 1 to 2% error rate. In contrast, Spring Boot had a few errors, but still remained stable overall. Django and Laravel experience significantly higher error rates, but it's still acceptable for Laravel. But for Django, it's maintained like 12.5% error rate due to amount of error because of its high load. Now, this is the numbers that we get from our research, as you can see. Now, from these results, we can draw several insights. Jin and ExpressJS clearly lead in terms of performance, achieving the highest throughput and the lowest response time. Laravel is slower but still stable under load, and Django has the lowest throughput and the highest error rate. This is because of the large amount of requests that cannot be processed by Django. For stability and speed, Spring Boot has a balanced option, moderate speed with reliable stability. And for developer considerations, Laravel has a strong ecosystem. It's good for rapid development, despite lower raw performance. Django, on the other hand, has rich ecosystem, but struggle for handling large amount of requests. Jin and ExpressJS is lightweight, fast, and reliable with high performance and high scalability, but requires more configuration and complex system. Now, the framework itself, framework choice depends on use case, browse speed, enterprise stability, or developer penalty.
So based on our findings, our recommendation for developers is to carefully select framework according to the type of application they are building. For high performance needs, Git and ExpressJS are excellent choices. For enterprise environment, Spring Boot is more reliable. And for rapid development and strong ecosystem support, Laravel and Django can still be available. In practice, organizations should also reinforce their digital strategies by integrating scalable backends with interactive applications to meet modern user demands. That concludes our presentation today. Thank you for your attention.
Nanti di framework kalian kan ada komposisi penilaian tuh kalau kalian jadi misalnya orang berapa kalau ini udah di kelompok ya kalian tuh jadi tunggu aja nanti dikoordinasi dari kalau pakai itu ada deadline kalau yang project biasanya bisa kontak berarti itu kan sehingga dari yang lain enggak iya jadi dalamnya projectnya kalau misalnya bisa berapa nggak kan kita yang aku
di yang submissionnya juga ada.
ya gitu pokoknya kalau ini ada di ini akan
Beda yang beda yang
Ada lagi yang mau ditanyakan? Lebih baik sih ada, tapi kalau nggak ada itu beli aja sih. Ya, ya, jadi biasanya ini diganti bentuknya link saya nanti kalau mau lihat gitu sih. Saya contoh, kita sudah nggak apa-apa ya, nggak Jadi datang saya menghargai partisipasinya selama 1 tahun ya. Sampai tahun ini kalau misalnya ada yang salah dari saya sama Pak Ikan, mohon maaf ya. Semoga sukses habis ini OJT kan ya. Dan semoga lancar OJT-nya skripsi ya. Biar bisa cepat lulus ya. Amin. Terima kasih ya semua. Waalaikumsalam. Question berapa? Jadi item ini nanti dibaca di bawahnya. Semua itemnya udah kita share kalian.
Dari mana terus di sini. Nama oleh